Welcome to this lecture. In this video, we are going to discuss different types of amplifiers and their models. In next few videos, I'll be discussing or introducing a new concept that is called feedback. To understand feedback, we should have proper knowledge of different types of amplifier. Thus, we are considering this topic as important for our discussion. Now let us start. The different types of amplifier. First important type is voltage amplifier. This is very common. We understand the voltage amplifier. We will discuss in detail. And next very common amplifier is, or popular amplifier is, current amplifier. Next one, transresistance amplifier, that also we will be discussing. We will also discuss Transconductance amplifier. So these four types of amplifier we will discuss in this video. There are other amplifiers like power amplifiers, class A, class B, class AV and class C amplifier, but those will not be discussed right now. So we will focus on these four types of amplifiers and we will try to understand their model. First, consider the voltage amplifier. For voltage amplifier, this is one voltage amplifier. Its input is voltage VIT and output could be V0T, and we can define its voltage gain as, so this is AV, we can consider it's the voltage gain, and it is defined by the output voltage upon input voltage Vi. Okay, this is the ratio of V0 and Vi is called the voltage gain of this voltage amplifier. Right? Apart from this, we need to understand the input resistance looking from input side for this amplifier, as well as another parameter, that is the output resistance looking from the output side, that I'll call it R0. So this Ri and R0, these two are important. This is your input resistance, okay, input resistance, and this is your output resistance. So these two will be useful for our model. Now how to include or how to get the model for this amplifier. So what we will do, so as this input side is the voltage, okay, and input resistance first I will draw. So this is the input resistance, that I will call it Ri, and input voltage, this side voltage, we will consider it is Vi. Now in the output side, what is happening? So we need to get one output voltage V0, but here the gain is AV, it is mentioned. So I need to consider one control source. So this control source we need to consider, and it should be a voltage source depending on the voltage Vi. As its gain is AV, I can write it is AV times this Vi. This is your dependent voltage source. Basically, it is a voltage dependent voltage source or voltage controlled voltage source. So this we can call as this one, voltage controlled voltage source. Okay, that kind of model we can consider here. Next, we need to include this output resistance, as we have considered the voltage source here. So the resistance should be connected in series. So whenever you will get a voltage source, its source resistance or any resistance, corresponding resistance, should be connected in series with this source. Okay, so this is your output resistance or not. So this is the model for this voltage amplifier. this one. It is very simple. It includes one input resistance Ri, one output resistance R0, and one gain AV that will consider in terms of voltage control voltage source. Now, in this voltage amplifier, we need to apply one input voltage, practical voltage source. So here, this is the input side. So I can include one input voltage source that I will draw. So it's a voltage source I need to consider. I'll connect with this one and with one source resistance. So this source voltage is our Vs and source resistance is Rs. Similarly, to get this output V0, we need to consider one load, and that load here I will consider one resistive load. It's one resistance only, and that is connected toward the output side. So this load resistance, I'll call it RL. So this is the output, exact output voltage across the load, that I'll call it V0. Now this overall voltage gain we can find out. So first we can find this Vi. You can look at the input side. This Vs, Rs and Ri, they are connected in series. This is independent from output side. So easily we can find out Vi, which is across this Ri. We can use potential divider circuit, because with this source Vs, we have two resistance Rs and Ri, they are connected in series. So voltage across Ri is Vi. So what is Vi? That's simply a potential divider. The voltage across Ri, the self resistance Ri upon total resistance is Rs plus Ri, these two, times the supply voltage, that is your Vs. So total voltage is shared across these two Rs and Ri, and across this Ri, the voltage Vi would be the self resistance Ri upon total resistance Rs plus Ri times Vs. That's simple. And same thing we can do for the output side. So what is the voltage V0? The voltage V0 will be simply the voltage across the RL, means this is the now source AV into Vi, is the voltage, input voltage, okay, for this network. So to get the voltage across RL, we need to consider RL upon total resistance, that is your R0, this R0 plus RL, times supply voltage here, in this case AV times Vi. Now you can replace easily this Vi in this case here, and then you can find one expression for this V0. So easily you can see that. So this V0 upon Vs. So can I find V0 upon Vs in total? That is very easy. So you can see this is one AV that will be there, and this factor is already there, RL upon R0 plus RL, and with this, so this factor will be coming Ri, because we are going to replace Vi by Ri upon Rs plus Ri. Okay, and this Vs already I have taken here. So this is your overall voltage gain, considering practical input voltage source and load RL. Okay, so this overall voltage gain, our interest is that to get maximum overall voltage gain with this practical input voltage source and practical load resistance RL. And you can see that these two factors are important. And these two factors, so first factor, if I consider RL upon R0 plus RL, so this is always less than 1. So at best it could be close to 1. So if R0 is chosen very low compared to RL, so condition is that if R0 is very small compared to RL, then you can see this RL upon R0 plus RL is very close to 1 because R0 is negligibly small. RL upon RL, they will cancel, its value will be close to 1. So this is one requirement, that R0 should be very less compared to RL. Similarly, the second factor, this Ri upon Rs plus Ri, that will be close to 1 if and only if this Ri is very large compared to Rs. So this Ri is very large compared to Rs. What is the meaning? The input resistance is very large compared to the source resistance, and output resistance of this voltage amplifier should be very small compared to load resistance. Then it is good for voltage amplifier. And in ideal cases, this Ri should be infinity and R0 should go to 0. This is for ideal voltage amplifiers, right? Now you can see that these two things, now this R0 and Ri, they are very important and we can choose in this proper way. And if it is not proper, then we can use certain feedback configuration to make it better. That we will be discussing in the other videos. Okay. So this is regarding voltage amplifier. Similarly, we will discuss current amplifiers. So next hour is current amplifier. So here we need to define first the gain. As it is a current amplifier, the gain we will consider as, so AI is the current gain. We will consider output current I0. So this one, this is the output current, it is going output side. We are assuming that something will be connected, load will be connected, that time we will be getting I0. Okay. And the input current, this is II. These two ratio will be called as the current amplifier gain, AI. Similarly, similar to the other previous one, that we should introduce the input resistance for this amplifier, current amplifier, that is Ri, looking from input side, and also we should have one output impedance for this current amplifier R0. So now our model, so you can see that this is your input side current II. I will take this one as reference. Okay, and now I will connect the load, this input resistance Ri. Okay, and this is common line. I will call it, consider grounded, input side and output side. Now as this I0, I need to consider one I0, one dependent source again. But this time it should be a current source. And this, its magnitude depends on this II. So I0 should be AI times II. So this should be AI times input current II. So what is this actually? This is a dependent current source depending on this input side current II. So can I call it current dependent current source? So this I can call current controlled current source. This is the model, we can use it. Now this output side I have considered one dependent current source. Now I want to include this output resistance R0. How to include? Whenever you will get a current source, the resistance will come across this current source. Okay, the Norton equivalence network you should consider. So what you will do, what we will do, these things, that with this we will consider one output resistance R0. It is connected across this current source. So this is very important. Whenever you will get a voltage source, the corresponding resistance should be connected in series, and whenever you will get a current source, that resistance should be connected across the current source. Okay. Now we will consider the input. This is the input side and this is the output side, and output side should be connected to a load. This is your RL, and input side, it should be a source, current source, practical current source. What is this? One current source, and that may have one source resistance Rs. Okay, so that I'll include here. You can see this is your source, current source, and its value I'll consider Is, and this source is having one source resistance. As I said that it should come across this one, and its value I'll consider Rs. And output side I am considering the load, that is your RL. Now this load current, that I'll call it I0, actual current available at the load. So overall current gain, we need to find out this I0 upon Is. This is your overall current gain. So AI, this is, I can write overall current gain for this network, right? Now we can find out the expression for this very easily. For that I need to get first II. So what is II? How can you calculate this II? So it is a current divider. Total supplying current is Is. It is divided by these two branch. One is through Rs, other is through Ri. And the current through Ri, easily we can find out that it depends on the opposite resistance. So it will be the opposite resistance Rs upon total resistance Ri plus Rs times the supply current Is. That we have discussed in detail in my previous videos in circuit theory lecture. So if you have confusion, please go through that one. So it's a current divider. Current through this branch will be the opposite resistance Rs upon total resistance Rs plus Ri times this supply current, that is Is. Okay. Very similarly the output side. To get this I0 means current through RL, we need to consider R0 upon, opposite resistance is R0 upon total, that is R0 plus RL times the supply current. Now it is AI times II. Okay. Now you can replace this II from here. Then you will get Rs upon Ri plus Rs times Is. And that Is we can divide here. So again you will see that we will be having two factors along with this AI. So what is this? So this one, easily you can see that the first term is AI, the open loop current gain for this amplifier, okay, without any load on input volt source. And then these factors, one factor is R0 upon R0 plus RL. Another factor is this one, it is coming from this one, that is your Rs upon Ri plus Rs. Again, you can see that this value is always less than 1. Its value is again always less than 1. Okay? Because numerator is R0 and denominator is R0 plus RL, and both R0 and RL both are positive. Similarly for Rs and Ri, Rs. Okay? So this value could be maximum close to 1 if and only if this R0 is very high compared to RL. Okay? So what is the condition for better current amplifier? That we are going to discuss right now. Okay? So this could be, if this R0 is very large compared to RL, then you can see that RL is negligibly small. R0 upon R0 is close to 1. Okay. So meaning is that this output resistance R0 is very high compared to RL, and it is making sense, because whatever current we are getting at this end, maximum current should go through the load resistance, and this, if this resistance is made very high, very less current will go through this side. So current will go through the lesser resistance path. So if R0 is very high, then maximum current will go through the RL only. We'll get maximum current at the output side, at the load. Thus, R0 should be as high as possible compared to RL. Very similarly here, R0 should get maximum current. So R0 should be very small compared to the RS, and that is also from here. If R0 is very small, then RS upon RS, it will be close to 1, right? Thus, this Ri is very small compared to RS. And you can notice that this input-output resistance combination, it's just opposite of the voltage amplifier. It's not same. In voltage amplifier, we have seen that input resistance should be as high as possible and output resistance should be as low as possible. But in this case, it is just opposite. Input resistance should be as low as possible. So ideally, this Ri could be close to 0. And this R0, for this one, it should be ideally infinite, very large. It is just opposite of voltage amplifiers. Please note, make a note at this point. Okay. Now we will consider transresistance amplifier. In transresistance amplifier, you can see that we need to consider what? This one. So we will define the gain of this transresistance amplifier. I will call it AR. It's a resistance. So resistance means voltage upon current. So numerator is output. So it's output voltage and input. So output voltage I will consider this way. This is your V0 instead of this one, right? And input current is II. So output voltage V0 upon II, the input current I sub I, this is defined by gain of the transresistance amplifier. Okay, so output voltage upon input current. This is very, very important thing. Okay, now again we need to consider input resistance Ri and output resistance R0. So what is our model? So now our model will be very simple. So first I need to consider input resistance. As earlier, it is your Ri, but it should accept this current II. Okay, so whatever II is there, so V0 will be II times AR. So here I need to get one controlled voltage source. This is a controlled voltage source, and its magnitude will be AR times II. AR times this II. As it is a voltage source, as I said earlier, then output resistance R0 should be connected in series. So it should be connected in series. Okay, so this is the model, and you can see here that in this case we have considered one control source. What is this? This is depending on the current II, and it is producing a voltage source. So current dependent voltage source or current controlled voltage source, CCVS. This model we have considered. Okay, it is depending on this current II. It is producing one dependent source, voltage source, thus current dependent or current controlled voltage source. Right? Now we need to introduce the input source and load resistance that we can connect easily here. So, but as it is a current, I need to apply a current source. That is important. So input is a current source. As it is a current source, it is IS. Its source resistance should be connected across it. Okay, and load we can connect here. This is RL, and whatever voltage will develop across the load, that is your actual V0. So overall gain of this transresistance amplifier, that is defined by this V0 by IS. This is your AR overall. Okay. So how to find this thing? Again, very similar methods. So what is II first? Okay. Can I calculate II? It's easy. So current through the resistance Ri. Again, total supply current is Is. It is divided by these two paths. One is through Rs, other is through Ri. I need to get the current through Ri. So to get this current, I need to consider opposite resistance, that is your Rs, by total resistance Rs plus Ri times supply current, that is your Is. Okay. Next one, to get this voltage, output voltage V0. So how to find this voltage V0? Now the source is this voltage source. Two resistances are connected in series, R0 and RL. I need to get voltage across RL. So same resistance, self resistance RL upon total R0 plus RL multiplied by this supply voltage source AR. This is your AR times II. Now this II we can replace here from here. Okay. So again you will be getting this ratio. Okay. This ratio will be now very easy. You will be getting, so actual value is AR without input and load. Okay. But with this, these two factors will be multiplied. What are these factors? One is RL upon R0 plus RL. Another one is this one coming from this one, Rs upon Rs plus Ri. Now you can see that to get maximum overall gain, this could be made 1. Again, this could be made close to 1. So what is the condition? So here condition is R0 should be very low compared to RL. Is right? Can you see these things? This R0 should be very small compared to RL. Okay. Because there should not be any drop across the R0. Maximum voltage should develop across the RL. Whatever voltage it is available here, its maximum should be available at the load RL. So drop across the R0 should be very small. So it is possible if R0 is very low. Okay. If R0 is very low compared to RL. Right. And similarly, this current II will be maximum if Ri is very low. Okay. Again, this Ri is very low compared to which one? The Rs. So you see that if Ri is relatively small, Rs upon Rs, it is close to 1. So you see the condition here. This condition is again defined from current amplifier and voltage amplifier. In this case, both the input resistance and output resistance both should be as low as possible. And this input resistance Ri should be as low as possible compared to the source resistance Rs. And similarly, this output resistance R0 should be as low as possible compared to the load resistance RL. Ideally, this Ri should be close to 0 and R0 is also close to 0. This is the condition for ideal transresistance amplifier. Okay. Now last one we are going to discuss transconductance amplifier. Very similar way we can define. So first we are going to define the gain. What is the gain? The gain would be A, we'll call it AG, transconductance. As it is a conductance, so numerator should be your current, denominator should be your voltage. So output should be current, this is your I0, and input should be voltage Vi. So the ratio will be I0 upon Vi. Okay, and we need to consider as earlier the input resistance Ri and output resistance looking from output side R0. So our model we can draw. So first we will draw always the input resistance, that is your Ri. whatever voltage is developing across this Ri, depending on that, we should get a current. So here I need to consider one current source, okay, which is depending on this voltage Vi. Its value will be, I naught will be Ag times Vi. So this value will be Ag times this Vi, because this is I naught, Ag times Vi. Okay, as I have considered a current source in the output side, the output resistance R naught should be considered across it. So this is your R naught, right? So this is our model. Now we need to include the practical input source and load. So input side we can include the source. So in this case it should be voltage source. Okay, I can consider this one. So input voltage source, it's the Vs, practical voltage source, and source may have some source resistance in series. That is your Rs. That's all. And output side we need to connect one resistance, that is your RL. So this is the actual current through RL, that I'll call it I naught. Okay, and this is your input voltage actually. So overall voltage, overall gain, transconductance gain. So Ag, its overall will be this actual output current through the load RL upon supply voltage source, that is your Vs. Okay, very similar manner you can calculate, you can find out the expression for this. So first we need to get this Vi. So what is Vi? Very quickly we can go for that. So you can see that voltage across this Ri. So self resistance Ri upon total Rs plus Ri times Vs. Okay. Similarly, I naught, in this case, this is a current source. It is dividing by this two branch current divider. The current through RL is I naught. So this I naught will be the opposite resistance R naught upon total R naught plus RL times supply current source. Supplied, this is Ag times Vi. Okay, so this Vi you can replace from here. So you will find the overall. So what is overall? So overall gain, transconductance gain. So you see that earlier it was Ag when there is no input connected, no load connected. Okay, but whenever you will connect, you are going to connect one input source, voltage source, practical input voltage source, and one load resistance. Now it is modified by these two factors. Okay, what are these two factors? First factor is this one, this R naught upon R naught plus RL, and second factor is this one, Ri upon R naught plus Ri. Now you can see that again, to get the maximum gain, we should make this quantity very large and this quantity also very large, close to 1. This is possible if R naught is very high compared to RL. So you can see that the condition is that R naught should be very high compared to RL. Then RL is negligibly small and R naught cancel out, will cancel out and it will give you 1. Similarly here, this Ri is also, Ri is made very large compared to R naught. Then also this quantity should be close to 1. Again, this condition is again not same as earlier one, just opposite I can say, to transresistance amplifier. So in this case, this both the resistance, output resistance R naught and input resistance Ri, they should be very high compared to the corresponding load resistance and source resistance. So ideally, this Ri for this transconductance amplifier should be infinite, and R naught for this transconductance amplifier, it should be also infinite. Then it is ideal, it is an ideal transconductance amplifier. Okay, I hope you have got this point, right? So in the next video, we'll be discussing, or in some video, we'll start discussing the feedback circuit, and there we'll be using this concept. I'll show you that feedback is generally used to make better amplifiers. Whatever it is, whether it is a voltage amplifier, current amplifier, transresistance or transconductance, we can have certain topology, certain configuration of this feedback circuit, we can make it better. Means, suppose right now for this transconductance amplifier, these are not an RI are not very high. So they are in kilo ohm range. Can I make it in mega ohm range? If it is in mega ohm range, obviously it will become a better transconductance amplifier. Feedback circuit can help us. Okay, I'll show you the topology, how to make input resistance and output resistance high for this transconductance amplifier. Please keep watching. So thanks for watching. We'll meet in next video. Thank you.